Hello, son. I'm happy to see you again after I think 2 months. So we are going to be doing today. We're going to be implementing the simple typed lambda calculus, which is a typed version of the untyped lambda calculus. In the previous episode of this series, we implemented like you can find it around here. There is a card probably. We implemented the classical untyped lambda calculus, an interpreter for it in OCaml, trivial stuff. But today we're going crazy. We're doing the typed one because we like types. It's OCaml. So if you like, please leave your like, subscribe. It's some of the buttons below here. Share it with your friends. Enable the notification bell. You know this stuff. YouTube. So let's begin. Uh, yeah, simple typed lambda calculus. This is going to flash in white in your eyes. Okay. Simple typed lambda calculus. It's made by Alonzo Church, the guy from the lambda calculus. It was introduced in 1940. So like 80 years by now. We're getting old. And it's essentially this typing rules. See, like, can I copy each one individually? No, I cannot. And as you can see, it's trivial stuff. It's like, yeah, makes sense. So first, I wanted to try to convince you that types matter. For this, we are going to be implementing. For this, we are going to go back to our interpreter, which was this. And for this interpreter, right now we don't have like any primitive. We don't have integers. We don't have strings. We can do like church encoding or any other encoding for numbers and etc. But it's not ideal, right? It's not like we can do much. Like we can do better than this. So to begin with, we're going to be introducing literals. Namely, we are going to be introducing integers, like an int, and of int. So that's it. That's how you do an integer. Now Camel is trying to convince us that it's bad and you should not do this. Yeah, and when trying to interpret it, you're going to notice that, yeah, that doesn't work. Because you also need a value for integers. And we could go like this. But here we're going to be doing something which is common in OCaml, which is every value now has a v before it. So we know if it is an int, it's like an expression. And if it is if it is a v int, it's a value of an integer. So we can go here and do this. Now this should be v closure, v native. And here lies the problem. Okay, so you have an application, you're calling a function, and before, sure, it was always a function. There was no other representation that you could do on this, but now you can. So what happens if this is an integer? Wow, this is where we go crazy with JavaScript. JavaScript so we add an exception called type error. No, that was fatal. And yeah, we ignore it and we say raise type error. We could also do something like invalid argument. Let's see, how is it done? Yeah, something like this. Vint is not a function. That is what JS does for you. But no one likes this error message, and it's better to not have an error message, right? It simplifies our lives, not as a developers, but as a if you're doing a programming language, no one cares about error messages. Okay, so yeah, now you have some weird stuff. Like sometimes before this function was total, so it would never fail. Now it can fail, and it will fail during runtime, and you have no way to know if it will fail or not. Like it's just untyped. It may fail. You may have a loop that goes, I don't know, 1,000 times, and one of the times it returns an integer instead of a function. You can also have a friend who likes you so much and do like a random function that sometimes return an integer and sometimes return a function. So yeah, we don't have types here. And this is a problem. Like I can do any piece of code. I need to fix down there, right? And yeah, it's just not ideal. I could, for example, add it here as a v1 and ignore this parameter. And let's try to run it. I think it's easy during exec to the ruling. Yep. And now we got a type error. Great. Programming. Let's enable the notifications. We can let's enable this text trace. We can confirm it that it happened on our line 27, 27. Yeah, that's about it. So this is the first thing that it's bad about not having types. But it can get way worse, especially here it's like just a loop. But imagine you're working with a bunch of people and you may think they're all smart, but sometimes you're like, I'm just lazy, I'm tired, I don't want to code, right? But they need to code and they do a bad job because everyone does it sometimes. That's part of the job. So yeah, we want to have something better. And this is where we introduce types. Because types are simple to verify, they're like verified over the code. So even if the code never finishes, typing still finishes, ideally, if it is decidable. And here it is. Not my implementation, but it happens. So we need to introduce types. Before introducing types, I'm going to introduce some modules. It's not going to be like the best of OCaml or something like this, but it's like as soon as you start to have types, you have a lot more complexity. So like this, is my OSP working? Oh, it should be. And I can open expression, right? So, but here I also want to introduce values, struct and we have an interpreter, terp, struct and what else do we have? So values should open expression, and interp should open expression and values. We can also go here and still keep like open expression and open values. But for now, oh, we also need to open the interpreter. For now, I'm going to comment this code because we need to do some changes to achieve the simple type of Lambda calculus. Okay, now we have something we can understand that we are not going to be playing with the interpreter today that much. It's mostly about types. So let's go back to the simple type of the Lambda calculus. Again, it's going to flash in white. I'm sorry. Just kidding. It's not this time. Uh, and let's read the typing rules. So it's saying that for a parameter, mostly in these typing rules, you can read it from like if the top, like if it matches the top, then the bottom. So it's like it's saying if x, then y. So like here, an x, when you see an x is mostly a function parameter, an abstraction parameter. I think even if you go to Lambda calculus, you can find it that, yeah, it's using mostly x here. But, well, here it's saying that if the parameter x has the type sigma, I'm not sure why it's sigma. I'm pretty sure it's sigma. I don't understand type theory. In this context, then the type then this stuff is true. So like in this context, x has the type sigma. Sure, that's yeah, that's how it works. And here I don't properly understand, but it's something about base types. It works, but this 3 and 4 is where it's interesting. This is like c is a constant of type t, then c t. Essentially, it's for literals, I think. So like if c is a literal, then c has the type t, and like we have int here. So like int has the type t, and the type t of int is going to be t int for us. It's the only base type that we have besides of. But we also need another type, which is described here. So like you have, if you have a context and you have an x with a type sigma and an expression with a type t. So you have context x of type sigma, an expression of type t, then the abstraction x of sigma with a body e is going to have a type from sigma to t. Essentially, it's saying that if you have a function from a sigma to e, and the type of e is t, then you have a function from a to t. That's about it. Don't overthink it. We call this t arrow. I think it's how we do in OCaml, and I think it's reasonable. T arrow. So it's an arrow type. You have two parameters in this type, left and right, and from two param type and body type. I'm going to be using param type and body type because I think it's like, maybe I'm repeating myself too much, but I feel like it's easier to introduce to people. And here we go with the last rule. The last rule is essentially saying if you have the expression 1 of type sigma to t, so like the expression 1 is a function from sigma to t, and we have an expression 2 of type sigma, like we have two expressions, one is a function, 2 has the same type as the parameter of the first function, then that means that applying 2 to 1 leads to the type t. That makes sense, because essentially you can think about it as subtracting types. So like you have sigma, sigma, subtract sigma, it's just t now. So that's how it works. That's how it works in OCaml. It's like OCaml has much more than the simple type at Lambda calculus, but you can still do this. I can make an example. I'm going to make the example later. You're going to see. So we need to introduce this. But to introduce this, first we need to introduce types. Which types? Here we need to have a constant type, anti-arrow. So let's do it. It's probably something like types. I'm going with type because why not? And type has the type of t-int, just a t-int or a t-arrow. T-arrow should be here because it's like more important. And it has a param type, which is also a type. And it has a body type, which is also a type. Like this. Oh, this is a bad idea. This is a bad formatting, but sure. And essentially, we have expressions and we have types. And both together, it's called a term, like you can see here. Like every term has a type when you have a type system. So it's around it. I think it's this order. So like term has type and expression. It's probably like this. If I'm wrong, please feel free to correct me in the comments. So now we have the types. How do we validate them? First thing that we need to introduce is that to follow this, you need to notice that all the parameters always have a type and an explicit type. We don't have full code inference, whole program inference like something like a Hindley Muller, but here, essentially, you just need to introduce param type. Open type here to you, and do type like this. Oh. And now every abstraction, every parameter also has a param type, and now we can proceed. Before proceeding, yeah, this is not happy. Let's ignore this because it doesn't matter to us. Yep. Now it's back to build again. And we can run the code still. It didn't change. We don't need to type it to run it. We can run it untyped. But yeah, it's not a good idea. I would not recommend you to do so. Okay, so how can we verify the types? Here on the simple type of the Lambda calculus, verifying the types is the same stuff as inferring the types. So I'm going to be calling inference because we don't need to declare the return type of functions and stuff like this. So we can do open type and open expression. And we are going to have a context. This context, before you can see that it's a context, like it's a value context. Here it's going to be a type context. So we can use the same functions, but it's like a little bit different. And we go with match expression. Let me close this, open here. Match expression with first first one is int. It's true. Yeah, we know int has a type t int. Again, following this rule. So int has a type of t, constant. And then next one we go with variable, like it's going to be a name. And we find the type in the context, so like name and context. If this type is not known, it's going to raise an exception. So I was like ignoring you before. This was actually not a total function. I was kind of lying to you, but I've like ignore this. Yeah, this is not total. It was not already, but now it's going to get even more clear that it's not total. Especially because now we have an explicit raise. We could do the same down there, but I'm sorry, I forgot about it. So here we go with abstractions, and abstraction is the third rule. This one. So we have a param type, a param type, a param type, and we have a body, and we have an expression. So as we know that every expression has a type, we can do body type, infer. To infer the body type, first we need to introduce we need to have a context, where we have context.add from type context in, and we're going to infer the body type using context and body. And now we can construct the type. It's going to be the arrow of param, and it's param type and body type, I think. Yep. Still progress. Now it gets to the problem, which is the last one, the last rule. The last rule, it's around application, and you can go to funct, an argument. And yeah, here it doesn't go well. You can build a func type, infer, context, function, right? One of the differences between the interpreter, one of the difference that you can notice between the interpreter and inferring the types is mostly related to application, because here you are not actually going to be running the function argument. You're just infer the type, and yeah, it goes well. You're going to see. And then we also have argument type of infer, context, argument, and the difference is going to show on soon. But for now, func type, argument type are going to match on func type, because again, we need to verify if it is a t int. Same stuff. You're going to have. Let me erase this type error up there, like here. We are going to raise a type error. So during typing, we raised a type error because, well, you cannot call an integer. An int is not a function. It doesn't work. So it must be a t arrow, but it not only must be a t arrow. It also needs to be like, you need to notice that here both of them, the param type and the argument type, are the same. So we need to verify if they're the same. How can we verify if they're the same? We could do in a couple of different ways in OCaml, but essentially we want a type equal. I'm going to implement it by hand, and later, again, you're also going to notice why this is important. Essentially, it's important because when you have a recursion, you want to break the recursion, and you want to have recursion types here, because, well, it gets worse without it. So the arrow, param type, param A, body type, body A, and also same stuff here, but P and B. And we are going to be doing, if they are equal, like if param A and param B are equal, then we do equal of body A and body B, so the types are equal, and otherwise it's false. I'm going to put this just for 1 second. And yeah, so you can see that this is actually comparing the types. So if the parameter of the first one and the second one are the same, they're equal. Like if the parameters and the body are the same, then they're equal. And if they are both an integer, then they are also equal. If it is like t-int and t-arrow or t-arrow and the int, then it's never equal. So with this, what you can do here is also you can go here and say when type equal of param type and argument type, when they are equal, we just return the body type. Otherwise, we just do raise type error and then remove this. So if it is a t arrow and the param type is the same as the argument type, then we return the body type. We could also do it, it in a bunch, like a couple of different ways, but I like this style of code. And now infer is already total, so we could play with it infer. But the important thing here to understand is that you can follow the rules and get to an algorithm easily. So like sigma and sigma must be equal, then we can verify it. So this can only apply if the types are equal and if E1 is a T arrow, right? So it's these lines of code. And the difference on here between this and interpreting the code is that here we just are comparing the types. We don't need to go over it again and again. If the types are like, if you have a loop, if you have a recursion and you have a loop, we don't need to check it again and again and again. We just check it once for the loop, and that's it. Then we know that it's not possible to raise a type error there. So if we have it typed, this function is total. Like if expression is typed, then there is no way for this function to ever fail, because well, the only failures possible here are related to types. So same stuff here. I can go and show you in more detail that the only possible ways for this to fail is with a type error. So type, and we're going to do this, and we need to go this. Okay. So yeah, you can see clearly that now this function, now you are seeing completely. And if this does not raise a type error, then this is total and there is no exception that it will ever raise from this function. We could abuse of this to build a compiler and make it more efficient. We could abuse of this to simplify our code. But for now, we are going to keep both versions. Maybe in the future episode, we can clean one of them. Maybe we can even compile it to assembly or something like this. Doing closure conversion will be a lot of fun. But yeah, let's try to infer it. To infer it and show you that it's working, I'm going to add a ppx. So it's like OCaml ppx arriving like this. And I think I also need to go here and add it. Where should it be here? ppx arriving, I think. So this is a nice ppx in OCaml. It allows you to, let me do easy, just to update. It allows you to derive things from types. And by default, it has the ppx that I want, which is called ppx deriving show. So like ppx deriving.show. Oh, I should not. I forgot about it. Just let's wait a bit. It should be fast. Okay, now it's done. It also updated some other stuff. Here it's done. Here it's also done. And yep. Now we can restart the language server and go something around here and do like deriving show. And now you can print your types easily. It's going to be really useful. Let's get a function, an ID function from an integer to the same integer. And to do this, you can do an abstraction. Param, you can call it x. Param type is also int. Oh, it's the int. Oh, I need to open all of this like here. And body should be just a variable x. So I know by looking at this that the type of this must be tint to tint. Let's see what is inferred. So like type, and we can go and do infer. Let's open infer and go x. Oh, we need a context. Empty context for now, it's going to be enough. And then we can print it using format printf a n like this. And it should be type.pp type and x type pp. Open value, comment for now. Let's run it. And yeah, you can see that it is like a little bit noisy. I think it's like show path equals false. Oh, path equals false. I don't remember how it's done. Anyway, you can see it's a little bit noisy, but you have a tint to tint at the end of the day. Let's look on the docs. It's arriving and show path. How can I? Oh, with path, not show path. It should be this. Where is my with path? False. And we can run it again, and now you can see a little bit clearer that it's a T arrow from an int to an int. So it did infer completely in the first try, which is nice, really nice. But yeah, let's keep going. Let's try a function application. So we know that this should be an int, and if I go here and I say I want to apply this function, so like a, and it's going to be application function. It's going to be x, and argument is going to be an int of 1. So the type of this should be an int, because we are just calling a function that returns an int. So I do infer. Same stuff, I can use context empty here, not a problem. And then I can print a type. Yeah, that's it. It's typing. Now we have we have inference working, we have types. How can we verify that something would be invalid? We can try an error, right? So if I try to call this with x, that should not work because x is a function and not an integer, and we get a type error. That's right. That's exactly what I was expecting to get. And so you can see that the code was rejected before even executing it. And we are going to go like even deeper. And I think we can type anything. I don't remember exactly, but I think with this explicitly we can type anything, not anything, but the basics of it. So let's go and try to do something with IO. So a useful function that it prints something. To do it, same stuff as same as last time. We go in initial context, but now we have a problem. We need two contexts. We have a type context, so like initial type context, and a value context. The value context is for the interpreter. The type context is for the typer. So the infer function. Here, print hello world before was doing an ID, but we don't have type variables here, so you don't have any kind of generics. Think about it as Go. It's as bad as Go right now, and I implemented it in like a couple of minutes. Great. So like let's do here. It's a T arrow from a from type. This from type should be. Oh, I forgot to open type. This from type should be what? From type should be. Oh right, it's a tint. I don't know. Sometimes it happens. Tint to tint. Yeah, that makes sense. And here it should be vnative. Yep. So for typing, now we do this, and for values we do the other one. So let's partially apply infer for now. Infer initial type context, right? And we can go here and we can go here, and it's still gonna no, now it's gonna work. But let's try calling print hello world. So if I go here and I say variable print hello world with argument like this, it should still be an int. Yeah, that's it. And let's try to interpret it by opening interpreter and the same stuff, interp and format printf. I can also add it. Can also add ppx deriving to values, which are it's useful. Yeah, I cannot because expression does not have one. I can add it here too, right? Can I? No, context does not have a pp. Yeah, context is bad. Let's do this by hand then. Let's print it by hand because, well, yeah. Let's try something. We just want to have a value pp here. It's not hard. You can do value pp, and a pp is this and plus a value, and I can go match value a pp and of n, and here I can print printf fmt of the d and n. If it is v closure, I can go and do. I don't care about it. I'm not going to open it. It's too much work right now. So it's just this, and vnative is just vnative too. So now we have a value pp, and we can go and say an like this. Let's do also interp initial value context here, and well, this we are doing this, and here it's gonna be value pp, and interp probably like this. So it should return 1, but it should also print hello world, and it does that. So the type is a t-int. It returns a value of type vint1, and it prints hello world. Great! But I need to prove to you that we have, we still have loops and stuff like this. But getting loops into the simple typed lambda calculus is tricky. It's really bad, actually. You don't know how bad it is because we don't have type variables, so you cannot have easily recursive types. Here, because we are out of the language, we can still do some stuff, and it's what I'm going to be doing. The idea here is that let me enable notification. Let me enable rec types in OCaml. For the ones of you who don't know, OCaml has recursive types just disabled by default. Because recursive types are like bad. It's an easy way to make the typer go into a loop and stuff like this. Especially if it is a complex typer like OCaml. And here we also have the same problem. I'm going to show you later. But let's do the first function that I want to implement is this. This function seems useless, but when you have this, you can essentially do a bunch of cool stuff. For example, you can do side effects. Because let's define it using the lambda calculus. It's like I'm going to do x and then y, and then here you can do just y, right? That's the same function. But what you can do now, because you have that function, you can do, for example, let's say you had snd, so snd dot, and we can implement here like this. So we have snd, and here you can, for example, do another function. Let's say we wanted to call print hello world is already, we could do print hello world of 1 and return 1 or 2. Like, the only thing from this that remains is the side effect. So we can do sequence of side effects because right now it's defined the order that it's going to happen and stuff like this. So it first this parameter, then this, so left to right normally. And because of this, you can do the next stuff, which is a loop. And to do a loop without using proper recursion, you can have the loop as itself. So I'm going to call it loop. And you can have a function, right? And here this function, it's going to be called with x. So we just want to loop and call this function with itself over time. We can go and say loop. But here lies the trick. Remember, we don't have like a semicolon like we have in OCaml. You can do s and d of f, x, f, loop, f, x. See? And I can translate this to the lambda calculus trivially. I can go and say loop dot, like here I was doing, I can do this for you to understand, b and b. And here I can go same stuff, f, x, and then I can do like loop of loop, and s and d of f, x, f, x. So you can see it's the same code. I would just add more parents. I would add way more parents by default. But this is not ambiguous, and OCaml can understand. But like, it's simple. But the thing that this allows you to do is that it allows you to pass a function that will be called forever, essentially. Oh, that's a better name, forever. Let me call it forever, like this. It's a better name. So it runs forever, okay? And yeah, like we had before. You can see the type here in OCaml is really going crazy. So BC of BC, B, D. So this is the same as this, but A is the first parameter. So this function is the first parameter of itself. I could define it in a better way. So like int between. Here they're using. Remember, we don't have like we need to type all of our functions. So I can go int, and then int to int, because we don't have type variables on our simple typed lambda calculus. And yeah, so I can say easily that this is forever, and I can do fun like this. Yep. So this goes forever, and that's what we need to do. But there is no way to construct this type on our current syntax. So I'm going to cheat a bit and do this outside of our syntax. First, let's implement SND. So like SND will be an abstraction that has a parameter, which is called B, and it has a param type of, here B must be a t arrow, otherwise it's not going to work for our use case, and param type should be a t int, and body type should also be a t int. Oh my gosh, that goes for a long time. You're going to see why. And we also have abstraction. I'm going to call it param A. And param type of A is like a t int. And body, it's going to be variable B. So you can see this is the same functions. They are the same function. The second parameter is B. The first one is A. Oh, the other is the opposite, right? It's B, A, I think. Because then you implement U, yeah. And the types are inverted. So t int and t arrow, okay. We can verify the type of this function by going and saying like snd type, infer snd type, infer snd, actually. Let's copy this. This is our abstraction. Probably the next episode is going to be, we are going to be doing a parser, because I hate writing AST by hand. Here I can do interp, infer, and snd, just to ensure the types are right. And yeah, there are. You can see that this is a t arrow, where the first parameter is a t int. The second one is a t arrow from t int to t int. And the third one, and it returns the same arrow. In fact, this would be closer if the signature was like this. now you can see why it needs to be like this, because we don't have variables. And so yeah, that's the same signature here and here. You can even see tint, so tint. 1 2 3 4 5, 1 2 3 4 5. So yeah, it's the same function, just in a different different abstraction. And now we need to do loop. Loop is the trick. To do loop, you need to have a type cycle, and I don't want to properly implement this, so I'm going to use a hack here using OCaml, which is, and actually I'm going to cheat because I implemented this before. It's not hard, but it's like, it's tricky. So here it's not loop anymore. I'm calling forever now. And let's compare this type to this type. You can see forever, like here. And then you can see that the first parameter after forever is this arrow, which is a int to an int. Enter body type returns tint, right? Here I was doing something a little bit different. So now we also have another step, which is like, we have a param type of tint and a body type of tint. So this is forever in the forever function. So this right here is itself. So like this is this. This is f. This is x, and this is the return. But remember, this return never happens. So we could put any type here, and it doesn't matter because it's never going to reach it. So it's not like it's unsound because the type never happens at all. You can also do the same in OCaml by going like a recursive function, like a loop, and you can call loop with unit, let's say, and you can see that it returns anything. But is it unsound? No, because to trigger this, you actually need to finish this function, and this function never finishes. So you don't have unsoundness here. But let's keep going. Now we have the forever type. And it's important to have the forever type because to construct forever, you need to have the forever type. I'm sorry. It's going to get recursive here. And forever is terrible. I had a partial, like I implemented it by hand because it's a lot and we don't have a parser. Don't you think it's great when we don't have a parser? So I'm going to call it forever. Forever depends on SND, right? So we can do SND type. I can go here and say SND type, because SND type happens before. So I can go and do SND type. I'm just being lazy. SND type. And you need forever type, which I'm going to call it forever. And F. Here we're going to be calling forever with forever. Let me, okay. I need to find the notation into here. So let's try to analyze this. So we are calling forever with forever, and then calling on the second parameter of forever, we are calling s and d with application of f. So here and x. Yeah, here's the difference. I'm doing x here, and I need to have another abstraction here. So like it's an abstraction of param x and param type of tint, and then the body is gonna be this. So it gets even deeper. Let's go deeper. Yeah, so here we have an application. We are applying forever first, and then we are applying SND. So this, and now we need to apply another thing, which is application funct. So this is our funct, and the argument is gonna be a variable x. Is it like this? Maybe I put it on the wrong stuff. Oh, here. Yes. See how it's simple? It's just like, yeah, forever, applying forever, then applying SND, F, applying X, and then SND, and then this, and it goes here, and yeah, that's bad, right? That's how you do when you don't have proper recursion in your, like, when you don't have a first class nice recursion in your language. Sure, we have recursion into Lambda calculus, but it's like this. See, how is it fun? Uh, it's not as bad if you're looking on the syntax, because then you can say, if you're just looking on the syntax, you can do all sorts of tricks. But we don't have a parser. That's why we're going to be doing one next. And then my goal is to be able to infer forever type, because we have forever type already. Can we infer it? Not yet. Let me delete the previous code. You're going to see why. So it's building, right? And Stack Overflow. Oh, why would this would be tail recursive? Typing it is not tail recursive. So it happens as Stack Overflow happens. It's expected it to happen because there is infinite recursion. So that's also why I implemented equal by hand, because I can easily do a short circuit for this case, which is A equals B and true. So like here I'm checking if the pointers are the same. So if the pointers are the same, then it means they are equal. And that's a short circuit. And this is gonna work. Actually, there is two possible, maybe this infer is gonna work. I don't think so. Let me look, let me remove this. Let's see if it just infers. It cannot apply it yet. Yeah, no. And there is also another one, which is when trying to print, it's also not going to be able to print it. Oh, that's it, because it's not able to print. But at least now they are changed. Now we are going back, we are back to PP type. And PP type is not recursive, because, yeah, it's not. So we cannot print this type. I'm sorry, it happens to the best of us. But you can understand that it's able to infer, right? I hope you can. We can do. Yeah, it's just so bad. You don't understand. When you have recursive types, you need to take care with everything. Otherwise, this just happens. Let's see if I can do any sort of trick to fix this. There is all sorts of tricks using an IDE. You can have, like, each type has an ID, and if you see the same ID twice, you stop, because now you have a cycle and you know what to print later. So I'm not going to be implementing it here. You can go and look on OCaml Typer how they do it. But for now, let's ignore this. We cannot print our type. We want to run it, right? So to run it, you need to call forever with forever. Not only that, because here forever also depends on SND. So it's more like SND than forever. But forever is already applied. So like, it's more like this. And then you do something like this. Let's expand it once more. You do like this. And what was, oh, we need to do SND. Where is SND? And this is SND. So like, you do something like this, and yeah, that's our code. See, so simple. Let's go. Let's ident it at least. And here we're doing forever with forever. So like this. And then, well, we are applying it. As you can see, there is 3 here. I'm gonna go and say it like this, just to make sure you can read it. Yeah, it's bad. That's why we also don't do Lisp here. So you can understand that this is actually right, because you are applying SND, then you are applying forever to forever, and then you just need to apply something to F, right? Let's try something, which is, I want to remove this type. So I know that it can infer it, but let's do an application, and let's apply forever to forever to have a better forever. So we can go and say the function is forever. We need to first apply SND, right? Yeah, but I'm going to remove the SND part from this, just to simplify. That's not the whole. Forever is just this. So you can go down there, remove it, and, well, there is still something off. See, there is so many parents. Can I remove it here now? No, I needed something like this. Where is it off? Subtraction. That seems to be right to me. Oh, got it. Now it's going. But yeah, what I need to do here is then apply SND to forever. But first I want to do okay, I need to go and do an application where I apply funct is forever, argument is also forever. So this is the first step. We have this, but we need to do an abstraction to apply SND. So we apply SND. I'm not going to add SND by hand in the context. Param is going to be SND. Param type is going to be SND type. Almost there. So body, it's going to be this. And you have an application, an abstraction, and we need to apply it. So I think that's how we get forever. See how it's complicated? Application, abstraction, and here it should be this is a function, and the argument is SND itself. Yo, that works, right? Great. So that works. And now this function already has forever implemented. And this is actually the forever that we want to have, because this is like, do I have the forever in OCaml here? Yeah. So when you have this function, which is what we had before, forever, let me implement SND in OCaml again, b to b, and you have fx, and you do forever, SND, fx, f, and x. When you have this, you can actually simplify it by doing forever of forever, like so. And then you have a function, which is the true forever, is just this, right? And this makes sense. You just pass a function, and you pass the argument, and it's never going to reach this, actually. So we could, for example, say it's a here. So that's the end step, the last one to getting our holy grail of types. And here I can go and do infer forever, I think. Let's try to run it. And it runs. Great. Can I print it? Very likely that not. So this is the true forever. This is the forever that I want to call. I'm going to do type, pp type, and infer. And here we do forever, like this. And you can print it. And it's exactly as I mentioned. You have the int, like the first parameter is a callback. The second one is an integer, and then it returns type. Can we call it? Yes, we can. I can also do interp to have the forever ready, but let's apply it with print hello world. Because remember, print hello world now is just a function from int to int that prints hello world. So to interpret it, I can do forever. Let's first do interp. Yeah, I'm going to go with forever. That's not going to give us anything special, just a closure, because we need to apply it. Let's do let's loop hello world forever hello world, which is an application of the function forever. Going to construct it with the argument. The first argument should be here we have two applications, but here's the first argument. The first argument should be print hello world itself, variable print hello world, like this. But we also need another argument, which is funct. And the argument here should be any integer. It doesn't matter. It needs to be an integer so that it can be inferred. But, well, it's about that. We do forever hello world, and we interpret it forever. Let's comment this to ensure that it's working. Int makes sense. And let's ensure that it runs hello world. So you have your loop, you have your Turing complete programming language with types. Please, if you liked it, this one was way deeper, and we got even into some typing rules. I just wanted to showcase how you can do crazy stuff. of course, you cannot define forever on our lambda calculus itself, because you cannot do this. This recursion right here is trickier. But if you had just plain old type variables, or like you have all sorts of tricks that you can do while keeping it simple. Uh, but well, we don't have it. I hope you liked it. I sincerely hope you like it. I hope you learned something, but this is a little bit harder. But yeah, if you learned something, if you don't, please leave your like, subscribe, enable the notifications bell. What you should also do, share this with your friends, share this on your job. Follow me on Twitter. Comment down here something. I don't know, YouTube stuff. So see you soon. Next one should be doing a parser for this, and then hopefully we can implement a Hindley-Milner type system, which is like a much fancier type system. We have generics then, and we also should be able to describe this type properly in the language. But yeah, that's it. See you all uh, in a week or so, or maybe in a couple of months. Who knows? Bye.